Welcome to science class. Today we are going to learn about Earth's layered interior. You no doubt know about the crust, mantle, and core, but today we will also be taking a look at the lithosphere, asthenosphere, mesosphere, and in fact there's an outer and inner core. Another job I have today is to demonstrate how we know what's down there. You can't go to the mantle or outer core, obviously. And why are we talking about this now, at this particular time? Well, keep in mind, Earth is both an open and closed system. Earth gets the energy for its open system processes from the sun, while Earth's closed system processes are powered by Earth's own interior heat. Plate tectonics and the features associated with it, volcanoes, mountains, earthquakes, rifts, etc., those are all created and powered by convecting heat from within the Earth. Let's get started. Let's start with what you should already know, the crust, mantle, and core. Well, actually, you probably don't have exactly the right idea about what those are. The crust is the solid top layer, the mantle is molten lava-like layer below that, and the core is a solid ball of metal. Wrong. It's not your fault. We get lazy and don't really explain things in their entirety. These three layers are compositional layers. The crust, of course, is solid, but it's not the only solid portion of the planet. In terms of composition, the crust is very uniform. We've covered this before. The crust is around 47% silicon and around 28% oxygen. In terms of rock type, most of the crust is basalt and granite, with basalt making up virtually the entire ocean surface and granite making up most of the volume of continental crust. The mantle makes up around 85% of Earth's volume. The majority of the mantle is solid, but incredibly hot. However, the mantle does deform and convect very, very slowly. The mantle begins at a point within the Earth where seismic waves abruptly increase their velocity. We'll come back to that later. The upper portions of the mantle are rich in peridotite, igneous rocks rich in olivine and pyroxene minerals. It's hard to be very sure about the mineral composition of the rest of the mantle, but we are reasonably sure it's around 45% silica and a whopping 35% magnesium oxides. The core is made almost entirely of iron and nickel and is around 2,400 kilometers in diameter. Keep in mind, it's not like the mantle abruptly becomes the core. In reality, the composition of Earth changes very gradually. There's no point where you travel 1 kilometer and all of a sudden, whoa, right there, it's totally different. We just picked a spot to say, yep, that's where we'll say it begins. The Earth's core is a two-layered system, both of which have the same composition, but different physical properties. We'll get to them in a bit too, but we're going to start on the surface. Earth has 5 what we call mechanical or physical layers. These are layers on the planet defined by their physical properties. This is what gives us 2 different cores, and the mantle is actually part of 3 separate layers. I've used the term lithosphere 42 times, not counting that one just there, so far in this course. Yes, I went and checked. I've sort of told you what it is, but here's my official explanation. The lithosphere is the solid surface of the Earth. The lithosphere is made of 2 parts, the entire crust plus the very top of the mantle. On average, the lithosphere is around 100 kilometers thick. To put that into perspective, if the Earth were the size of a basketball, the lithosphere would be 2 millimeters thick. The asthenosphere is the layer below the lithosphere. The asthenosphere is what we call a plastic layer, or a soft solid. It's not quite like molten rock on the surface. It's way more viscous than that, but it deforms easily. The asthenosphere is around 700 kilometers thick, and the entirety of it is made of the upper mantle. Without this soft layer, plate tectonics just couldn't happen. It acts much like a conveyor belt for the rigid lithosphere to move about on top of it. The rest of the mantle is what we call the mesosphere, and it's massive, about 2,900 kilometers thick. The mesosphere is rigid, but it convects. The convection is extremely slow, however. We have seen how rock layers can fold if enough pressure is applied over long periods of time, but we still don't call those rock layers liquid or soft. What helps deform the mantle is the temperature. At the deepest depths of the mesosphere, it's around 4,000 degrees Celsius. This convection, you'll remember, is the driving force behind what gets plates in motion. Ribbons of rising mantle rock break through the thinner, weaker oceanic lithosphere and drive plates apart. So the difference between the outer core and the inner core mechanically is that the outer core is liquid. There are other physical differences too. The outer core is around 4,400 degrees Celsius and has a density of around 9.9 grams per centimeter cubed. The inner core is as hot as 6,000 degrees Celsius, hotter than the surface of the sun, and has a density of almost 13 grams per centimeter cubed. The outer core is also much larger, 2,270 kilometers in radius compared to 1,200 kilometers of the inner core. Pressure, temperature, and density all increase with depth on our planet. As a matter of fact, the density of iron is less than 8 grams per centimeter cubed on the surface, and for nickel it's less than 10. So the specific gravity of 13 we find at the inner core means the molecules are being crunched with an incredible force. That crush is what keeps the inner core solid, even though the temperatures are much greater. Temperature and pressure don't necessarily increase at the same rate. In the outer core, the effect of temperature on the iron-nickel structure is greater than the pressure, so it's a liquid, while at the inner core, it's the opposite. Again, it's not as if there's a boundary where you're in a liquid metal core, then you hit a wall. The change is so gradual that there's no one point where it's liquid right there, solid right there. All right, now how on earth do we actually know any of this? Have we gone and checked? Well, the deepest hole ever dug is the Kola Super Deep borehole in Russia, right next to the Norwegian border. It is literally the most unimpressive site you could ever find for such an amazing record. The hole is 12,262 meters deep, so 12.2 kilometers. That's a little better than a tenth of the way to the asthenosphere, but it's less than 1/500th of the way to Earth's center. Volcanic material comes up to the surface all the time, but it comes from the uppermost asthenosphere. Still, only about 1/25th or so the distance to Earth's center. So obviously we have to make inferences based off of the best data we can get. But it really isn't much of a mystery at all what's down there. We can be very certain. I'll show you why. Thanks to Isaac Newton's mathematical genius, we can calculate what the mass of Earth is. And it's not even hard to do. The formula is incredibly elegant. Here's the formula for general relativity. I recognize pi and c is probably the speed of light. Other than that, I have no idea. But to calculate Earth's mass, all you need to know is 3 things. The gravitational force on our planet, which is 9.8 meters per second squared, not too hard. The diameter of the planet, also not very hard to find, square it, then divide this by the universal gravitational constant. Not as easy to find, in fact, Newton never did, but Henry Cavendish did so in 1798. But that simply goes on the bottom and voila, Earth's mass. Earth's mass is, forgive me for rounding, 6 with 24 zeros after it, kilograms. Now that we know the mass of Earth, we can calculate the density, which is just mass divided by volume. Earth's average density is 5.51 grams per centimeter cubed. We know the composition of the lithosphere and upper regions of the mantle, but those densities don't really go beyond 3.5 grams per centimeter cubed. Now, if we assume Earth is made almost entirely of silicate minerals and whatever else we find in the crust, you can calculate what the density of Earth at the core would be even with the increased density due to pressure. It would not get all the way up to a specific gravity of 5.51. We need heavier materials, and an iron-nickel core does that for us. But couldn't it just be a far smaller core made of much more dense elements like uranium or lead? Theoretically, the core of some planet could be that, but ours isn't. let's talk about how we know. So why iron and nickel? A few reasons. One, like we just covered, it gets Earth's average density to where it needs to be. But also meteorites. If you recall from our first Earth science video, I gave an appallingly brief account of how Earth and the other planets formed. Planets and moons are made of colliding debris in space: comets, meteorites, and asteroids. Technically, I should say meteoroids. That's what they're called in space. They become meteorites when they hit the Earth. But anyhow, we have thousands and thousands of meteorites we can study. They come in many different varieties, but they give us insight into the kinds of materials that make up rocky bodies, like planets and moons. Iron meteorites happen to be pretty common. Earth is, in fact, mostly iron. You should remember that the reason nearly all of this material is in the core is from differentiation. Another reason to assume an iron-nickel core is Earth's magnetic field. There are only a few elements that exhibit magnetic properties, mainly iron, nickel, and cobalt. Earth's rotating core of mostly iron generates a magnetic field. Some of the convection that occurs inside the core is likely important too, but the planet's rotation itself is key. Venus, which is very nearly the same size of Earth and almost certainly has a core like Earth's, doesn't have a magnetic field because it takes 243 what we call days to rotate. Much like a slow-turning generator doesn't produce much electricity, a slowly rotating core doesn't produce much of a magnetic field. Okay, to finish up here, let's talk about how we know where each of these layers is. That revelation came from studying seismic waves. At a certain depth, seismic waves increase in velocity. This is strange because they lose energy. Why should they speed up? This increase in speed comes from the wave transferring into a different, more rigid and dense medium. This boundary marks the transfer from the crust to the mantle and is called the Mohorovicic discontinuity, after its discoverer, Andrija Mohorovicic. But you can just call it the MOHO. To understand this a little better, think of how energy travels through different materials. Picture water. You make a splash at one end of the pool, and you can watch the energy travel through the water. It's not a very solid material, so the energy moves fairly slowly. Now picture a spring. Actually, I have one. I'll do it for you. You can see the energy transfer through it. It moves pretty quickly, but you can still see it happening. Now picture a very long stick or something very rigid. You give it a push, and the far side moves. Not instantaneously, but it looks instantaneous. For the record, the maximum speed at which energy travels through an object is whatever the speed of sound through that object is. If I had a 1 kilometer long meter stick and I pushed one end of it, it would take almost exactly a quarter of a second for the other side to move. Let's go back to the spring. You can see that if I tighten the spring, the energy moves through it more rapidly. I'm not making the material more dense, but I am making it more rigid, and it has the same effect. Seismic waves continue to increase in velocity through the Earth as the Earth gets more dense. That is, until they don't. Right here at the outer core, seismic waves lose about half of their velocity. What gives? Well, remember, the material is a liquid at this point, so it's not as rigid. A dense liquid is still less efficient at transferring energy than a much less dense solid. Notice how the seismic waves do increase in velocity throughout the outer core, and then their velocity rockets back up at the inner core. Oh, and we know the precise depth at which each of these things occurs also. Another reason we know the outer core is liquid is because S waves cannot be picked up by seismic stations on the opposite side of the globe, but P waves can. P waves or body waves are compression type waves that can travel through any kind of material. S waves can travel through the rigid mantle and crust, but they are stopped at the outer core. However, some seismic stations don't pick up any seismic waves at all, even if they are closer to the epicenter. What's that all about? It comes from the deflection of waves by the boundary of the outer core. As the speed of the seismic waves changes, so does their vector. That's why we say velocity more often in science, because velocity is speed plus direction. So this P-wave shadow zone, as it's called, is caused by Earth's outer core. Do some simple calculations and you get a sense of the precise size of the outer core. You see, we really can see into Earth without actually having to go there. Next time, we are going to begin a unit on historical geology. Get ready to take a dive into the entire 4.5 billion year history of planet Earth. Thanks for watching.